Thank you very much. Thank you very much for inviting me, and thank you for organizing such a great event. Highly appreciated. Thank you. Yes, before I start, I would like to point out at least some of my collaborators. Some I will point out later on again, but I would like to point out Felix Nüske and Sebastian Peitz in particular, who, conversations with those two essentially got me into all these Koopman related work. And yes, it's really a pity that they can't be here, but sending warm regards to all of you, in particular from those two. Okay. Then 10-second announcement. There's a nice topical collection on data. Oh, what have I done? on data-driven systems and control, analysis, modeling, optimization, and stochasticity from this very nice journal, Mathematics of Control, Signals and Systems, and it's still open for submission if you want to. Okay, what am I going to talk about today? So it's on kernel approximations of the Koopman operator and their use in predictive control or control in general. To that end, I will very, very briefly touch the Koopman operator and EDMD just to introduce my notation, I would say. And then I would briefly like to chat about probabilistic finite data error bounds on the estimation and projection error, and afterwards going or proceeding with kernel EDMD to get uniform bounds on the full approximation error, because from a control perspective, we would always like to get closed loop guarantees. And that means we have to somehow deal with the error, assuming that one is present. Okay, so extension to control, that's something already Igor and Mircea already addressed a bit. There are different options. And in particular, I think it's very appealing, this Koopman framework, because if you look at something like model predictive control, you naturally have to do predictions of your dynamical system. Of course, they will depend on chosen sequences of inputs actually. So yeah, that was the storyline since I did model predictive control for quite a while, which made me, which motivated my research in the Koopman operator. And in particular, there I would like to revisit these error bounds, making them proportional, which is actually from an analytic point of view quite easy at that point, but that precisely gave us the right notions in order to leverage all that in the control context. And finally, I would like to get closed loop guarantees. Probably I will run out of time for this control part in the very end, but there's a nice overview paper where you get pointers to the respective literature, and I'm also happy to chat with all of you about that. Okay, we have a nonlinear dynamical systems. Let me start with the autonomous case with respect to these error bounds. X plus equals to f of x, and I can make this a bit shorter. I assume that the dynamics is unknown, so I would like to have a data-driven surrogate model. That's my goal. And then I would like to predict some observable or quantity of interest, for example, state constraints or some cost function at some future, meaning here, successor state of my dynamical system. And the Koopman operator goes the other way around. So I start with the observable, I propagate more or less an observable, and then I have this nice Koopman identity all of you are very familiar with. Of course, you can do it for continuous time systems as well, so I will jump back and forth from time to time. EDMD, also this is something I can make very short. So we have typically a finite set of observables, let's say capital M, and then I collect data on some compact set. And typically I have observable data and observable data at the successor state. And using these data, I set up my data matrices and I solve some regression problem in order to compute some kind of empirical estimator on that compression, meaning first restricting the Koopman operator to the respective finite dimensional subspace, and if need be, so if it's not somehow Koopman invariant, then you have to project back. And this projecting back, of course, induces some projection error potentially, and due to finitely many data, I have some estimation error here. Okay, so what can we say about that? When I started with all this Koopman business, I would say I haven't found much on finite data error bounds. Later on, I came across Igor's work, and I think that's, to the best of my knowledge, the first one who specified like finitely many data. That's my approximation error. So there are some other authors as well who looked into a similar direction, Enrique Zuazua and co-workers in particular. And we also did that and extended it to control systems and to STEs. And then, of course, there's a series of papers, not only by us, but also by others like Alex Moreau, Stefan Klus, who's coming later on, further relaxing the required conditions, stuff like that. But what you get some bound on this estimation error with high probability. You can analogously do that for the Koopman operator. And then you have different sampling regimes, typically IID. From a mathematical point of view, also very nice is ergodic sampling, which fits very nice to dynamical systems. For control system, that's a bit of a challenge, but there are some approaches, if you look at Todd Murphy's work, others who try to somehow imitate ergodic sampling for control systems. So that's quite interesting because that's much, much cheaper, because then you can simply sample along a trajectory. And if you think about robotics and I impose IID samples, you will tell me, oh, that's not very practical. That's really painful. Please do something else. Okay, what you then get, here you see we have the Frobenius norm, so that's nice. That's really a uniform error bound. But for the projection error, we only get an L2 error bound typically, like Enrique Zuazua did it in his work, leveraging techniques from finite elements. But then, as you know, you analyze the Koopman operator, the generator setting, you have a transport equation, you have a hyperbolic partial differential equation. So that's what you can expect by simply using some dictionary of finite elements. So you have to come either up with a smart dictionary using eigenfunctions or more sophisticated techniques even there, or somehow deal with this invariance problem differently. Okay, so that's what I already mentioned. And then you can extend that, so that's not related to this finite dimensional deterministic setting. You can do that for time homogeneous discrete time Markov processes, including stochastic systems. So far, that's quite nice. And here is a nice computation for some SDE, so a 35 amino acid protein done by Felix, and nice computations for PDE, the Kuramoto-Zybaszynski equation, done mainly by Sebastian. So somehow that works nicely. Okay, two aspects I would like to point out in particular, because I think they could point towards interesting future research. So the first one is pretty well known, but anyway, here you have this Koopman operator identity. But if you look at that, you have this nice compact rectangular set, you lift it, and of course the true Koopman operator lifts this state trajectory to some trajectory on this nonlinear manifold. And then typically we come up with some kind of a linear operator, which could even be represented by a matrix in many cases. And what you typically see, you do not preserve this invariance as long as you don't have eigenfunctions only or something like that. And that means we have to get back. And if I trace it back correctly, but feel free to correct me, Alex was one of the first ones to properly mention that in his papers, I would claim. And Mircea also pointed that out. If you include the state in your dictionary, then it's clear what you could do. You could simply use these state components, go back to the Rn, and lift back to this nonlinear manifold. So there's a natural way, let me call it coordinate reprojection, because you are projecting back to this nonlinear manifold, which ensures that your next state is again consistent with your lifting, meaning if you have x1 and x1 squared, that works again. And so that's good, but you could do it more sophisticated, I would say, which is also nice. So we did something with Peter von Gore and Rob Mahoney using some differential geometric arguments. So that's quite nice because then you have a natural maximum likelihood estimation for determining the state. And you could argue it's not so impressive if you do a one-step prediction, but if you do a multi-step prediction, that really pays off because you can easily propagate this maximum likelihood interpretation as well. And so that's quite nice. So you can propagate these covariance things. Okay. Nevertheless, it points out you have to come up with suitable dictionaries. That would be great. There are different approaches, and it points to, correct me, I think your third problem, what can we do to relate it with AI? And nicely contributed there, coming up with very good liftings, but sometimes it would be interesting to even better understand them. What is AI bringing or providing? Okay, so that's the one issue I would like to discuss later on with some of you. And the second thing is you could go to reproducible kernel Hilbert spaces. And I will tell you in a minute why. So I think also that's something I do not have to repeat very much. Most of you are quite familiar with that. So we are on a Hilbert space, and in particular, we have this reproducing property, meaning a point evaluation is well specified. So that's what we need in control anyway, somehow. I would like, if I have a robot, then I have to do a point evaluation. I have to make sure that I'm not running into this wall. It's not good to have only an L2 measurement or bound. Okay, and then naturally you have these data points, and these half-evaluated kernels provide your finite dimensional lifting in this. Yeah, and then you can extend a EDMD to kernel EDMD, so that's nicely done. But what about the approximation error? And what you see here is I'm doing that in a non-standard norm, you could say. When I chatted with Matt Colbrook, for example, he's typically always doing it in L2, 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 or did it. Now he's also doing something like this, so that's nice. Because if you do it L2 to L2, he has rigorously shown, I think you were also involved, this complexity solvability index, and you need two. So you have two limits, infinite lifting and infinitely many data points. And the cool stuff here is we only have one limit, and that's due to using another norm. Then we squeeze in some term, of course, so simply the projection of the Koopman operator and so on. And then we have to analyze all these error terms. One is easy, projection. This was also easy, that's standard. Then we have these terms. They are nice. You probably can do it more efficient. Maybe Petter will tell us more about that. Let's see. But let me do it in a quite standard way. So we resort to the fill distance. We resort to approximation theory. It's not yet highly data efficient there. Petter will tell you us more, maybe not. Then you have to ask him at dinner, whatever. But here, that's the reason why we use these Wendland kernels in order to leverage approximation theory in order to get this plus 1/2. You could do it with Matern kernels as well, then you lose an order there. And that was a key step for us. If you look at this Koopman operator, mapping, now I did it in the general fashion on this slide. So we have a map from X to Y. So the Koopman operator is mapping from the native space on Y to the native space on X. You could equal both spaces if you want to. But now we have a finite norm. And that's due to the choice of the kernel. Matern kernel is also doing that, but you can't go with a Gaussian kernel here. That's critical at that point. And doing this leads to this inclusion. So our lifting is not Koopman invariant, but our native space is Koopman invariant. And that's quite nice. That's a key reason why then we can analyze the full error using this approximation theoretic results and by using this identity to some Sobolev space. So that's nice. And you can also do it using proportional bounds. That's essentially quite easy because you see directly how to get from here to there this distance from X to the set of data points is always smaller than the fill distance per definition. But that's what we need. So meaning we have to, if we would like to talk about set point stabilization later on, we need to include our set points in the set of data points. And then we know that we are 0 at 0, no approximation error at the data points. That's what we would like to have. And that's quite natural in this RKS, because there this regression problem is indeed an interpolation problem. Igor is already looking at his watch, so probably I have to speed up. No? Good. Good. So simulation ways, that also nicely fits. We did something similar to Mircea. So we decreased the fill distance and checked whether it gets better. So somehow, yes, somehow you could claim no, what is happening there? It's Lagrange interpolation. You can think what we have to do in order to resolve that using a different grid. So I would say a Cartesian grid of Chebyshev points would do it. If you do it two-dimensional, you can do it in an optimal fashion from a condition point of view, then it's a Padua grid. And that's what you can see here. Here you really see a nice decrease of the full approximation error. That's what you can also see in this line. But if you go here and you are mainly interested, or if you would simply say, oh, at the boundary of my set, maybe the error can be a bit larger, yeah, then this Lagrange interpolation is also nice, because here, closer to the origin, where you have less margin for error, if you think about Lyapunov arguments typically, then that could also work. Okay, you can extend it to regularization, clear. And yes, so far, that's the part on error bounds. And that's what I would like to leverage in this control setting. Maybe because it's more on a Koopman workshop and less on a control or model predictive control workshop. Let me briefly recap MPC. MPC is very easy from a conceptual point of view. That's also, I would say, the key driver for its success. So if you're driving a car, you obtain more or less a state measurement, as good as can be. Then you predict your system behavior on some finite horizon. You optimize the sequence of inputs. That's what we had in Igor's talk already. And you apply the first one of these optimized input sequence. Okay, and then you close the loop, meaning you measure again. For example, a car is broken down behind this curve. Then you should replan. And that's what you could do, because you again predict, optimize, and implement only the first bit of it. And the interesting point of view for me is what happens in the long run. Do I really stabilize the system? What happens due to this finite prediction horizon I only have? But that nicely fits to all what I presented to you before. On finitely many and predefined finitely many steps, I can deal with the error. So I only have to include my error analysis in my techniques in order to show, for example, closed loop stability, stuff like that. Okay, similar stuff for the MPC algorithm. I don't want to do it in details, but here again, we have our costs evaluated along the state trajectory, and we could have something like state constraints. So somehow canonically given or quantities of interest I would like to predict. So that nicely fits to the Koopman framework. I think this is also something I can do very briefly because it was pointed out several times before here, and it's nicely done in this paper by Jacob Todd and Martin Chokens. Even if you have a dictionary of eigenfunctions for the autonomous part of your system, it's not so clear how it propagates to the control part, because you have this part, so that works nicely in the generator setting, but then you naturally couple the derivatives of your observables with the remainder of the dynamics, meaning even if that's a BU, so a state-independent part, you will get some kind of coupling. And that tells us we have to take care of that. There are different approaches. Let me keep it short in order to come to some other things as well. Anyway, there is need, and I think that was pointed out in several talks already, to really yes, somehow close the gap under which conditions you get along with linear control surrogate models, because that would, of course, be highly attractive. If you can do it, you should. Sometimes you should question how far you can go with that. Is the domain of attraction limited? Whatever, you could discuss. But in practice, there are so many successful demonstrations. We have to fathom out these phenomena and to really get to the point where we can clearly say, where do I need all this nonlinear theory? If you go back to classical control theory, PID control is quite good up to now. So I would say 95% of all applications work already there with linear models. But there are some applications, particularly for robotics, where you have to come up with smarter things because the linearization doesn't give you enough information. With Koopman, there's hope that this gap is even smaller because you have a lifting in addition. So, but yes, somehow speculative. So I would like to emphasize this control coherent modeling framework, which we have in our workshop as well. So that's nice. I would emphasize this reprojections. You don't want to include it in every step, but maybe every 20, 50 steps in order to ensure consistency between your data and your current predicted state. And what also works are these kernel EDMD for control approaches. There you have rigorous error bounds, but you run into a bilinear setting. So there is a price we are willing to pay. There are examples where it's worth paying that price due to much better prediction capacities. We also tried to verify all the things on real-world systems, so some custom-built robots. And there you also see if you don't do any reprojection at all, at sometimes you are off typically, but for a while it works quite nice. So there's something in between. And if you want to see the current state, it's there in this paper, but that would be another talk, which I don't squeeze in the last 3 minutes. And yes, as I emphasized, you could extend more or less, I would say, everything I told you with respect to error bounds to the control settings, but only to the point where we have bounds on our particular predictions. Before, what I presented so far are really bounds on the full Koopman operator. So that was quite nice. Here, you have particular dictionaries similar to what Mircea told you. You include the state and so on. You would like to make your particular predictions reliable. That works. You can then flexible sample. You again have something like a proportional error bound with respect to state and control. And the nice thing is you can, by here, decreasing the fill distance, for example, adjust these constants and then make it work for your particular setting. Of course, the computed constants are very conservative. As always, I would say. Then numerical tests showing that it really works. Yeah, but let me revisit that once again. It's a slide by Robin Stresser. So these are some of my collaborators I haven't mentioned right in the beginning. So Robin Stresser, Julian Berberich, Frank Algebra, I would also like to mention, and also Igor in that context. We teamed up recently for a nice paper. And yes, so we have a nonlinear system. We have open loop predictions in MPC, for example. You have a surrogate model via EDMD. So that's nice. And you design a controller, for example, an LQG. It works nicely, set point stabilization. But the key question is, will that controller also work on my original system? So that's what I'm actually asking or interested. And that's not always the case. So there you have to take some care. That's the main message of the slide. And then I have 2 more slides demonstrating that you can resolve these issues, for example, for model predictive control due to or leveraging these error estimates. I will skip the details right now. Feel free to approach me later on, I would say. And then we demonstrated that it also works here for this 4-tank process, for example. And what you also see, if I would like to stabilize the origin, then it's not a bold conjecture to say, okay, the origin is an equilibrium for that control value. I should include that data point due to this interpolation property if I would like to get to a very high precision in the end. Okay, so let me conclude. Finite data error bounds. I briefly presented you probabilistic error bounds, then going to kernel EDMD and using this invariance of the respective native space, you get uniform bounds on the full approximation error. I promoted somehow these reprojections. I'm a fan of that, I would say. Then you can have these, you can use proportional bounds. That's what you typically need if you really would like to have asymptotic stability instead of practical asymptotic stability. You can do it in a predictive control fashion, or you could directly design controller. I would say I can again reference to Mircea, who gave you some of the details, which are then quite similar, and otherwise you find them in this preprint. Okay, thank you for your attention, and